We learned about the standard enthalpy change for a reaction. It was delta H with a degree symbol here, reaction. That was the change in entropy, enthalpy, not confusing at all. Entropy, energy, enthalpy. Change in enthalpy for a process in which all reactants and products are in their standard states. Remember hearing about that? Just to refresh our memories, the standard state definitions, a gas is, in its standard state, is the pure gas at 1 atmosphere of pressure. For a liquid or a solid, it's the pure substance in its most stable form. Some things have more than one form, like carbon can be graphite or diamond, whichever is more stable, at 1 atmosphere, and the temperature of interest, which is usually room temperature, 25 Celsius. If we have a substance that's in solution, we're looking at a concentration of 1 mole per liter. Those are the standard states. So the standard entropy change for a reaction, delta S, 0 for the reaction, is the change in entropy for a process in which all the reactants and products are in their standard states. So this is analogous to the standard enthalpy change. Entropy is a state function. It depends only on the entropy of the products and the entropy of the reactants. What we need is we need to somehow define standard molar entropies. We have to just define this because absolute values of enthalpy cannot be calculated. There's just no way to do it. Did I say that right? When we were talking about enthalpy, we had to define 0 because we couldn't calculate the absolute value of the enthalpy. But for entropy, there is an absolute 0. So this leads to the third law of thermodynamics. The entropy of a perfect crystal at absolute 0 is 0. So that would be a perfect crystal, nothing out of place, no contaminants in there. And at 0 Kelvin, all motion stops. Those particles are not even vibrating, right? So these are not vibrating. All of these are in arranged. There's only one way to arrange them, and they're all at 0 energy. And so we can say that that has 0 entropy, and we will measure from there. So entropy is an extensive property. It does depend on how much substance you have. So we're going to express entropy in joules per mole Kelvin here so that we can account for the amount. So we can look up standard molar entropy values in tables. So table 19.2 gives several here, and then there's a more extensive list in the appendix of your textbook. So are any of these perfect crystals at 0 Kelvin? Do any of them have 0 entropy? No, they don't. So at 25 degrees Celsius, the standard entropy of any substance is the energy dispersed in 1 mole of that substance. This depends on the number of places to put the energy. So that's going to be affected by the state of the substance, by its molar mass, the allotrope, is it graphite or diamond, the complexity of the molecules, and the extent of dissolution. Depends on lots and lots of things. The entropy of a gas is generally larger than that of a liquid, which is larger than that of a solid. And we mentioned this earlier, gases have more energetically equivalent ways to arrange their components. they are more disordered, right? So a mole of water vapor has higher entropy than a mole of liquid water. The entropy of noble gases increases with increasing molar mass. So here's helium at 126, and as we go larger in the noble gases, we see that the entropy increases. So energy states associated with the motion of heavy atoms are more closely spaced, and that gives more opportunities for dispersal of energy. You can only compare entropies if the substances you're looking at are in the same state. You can't compare a solid to a gas. You could only compare gases to gases or solids to solids. Different allotropes. So graphite and diamond are two different forms of pure carbon. The entropies are different because the arrangement of the atoms is different. In graphite, we have layers of carbon bonded to each other. These are both network covalent solids. And here we have hexagonal rings of carbon that are covalently bonded to each other, but the individual layers are only held together by intermolecular forces. Whereas in a diamond, we have a three-dimensional structure that is all covalent bonds. The entropy here is lower because those atoms are more constrained. They cannot move as much as the atoms here. So lower entropy, higher entropy. So for any given state of matter, the entropy will generally increase with molecular complexity, because now we have more places to put the energy. What does this mean? Well, if we think about argon, argon is an atom. It has translational motion. But if we look at my favorite molecule, nitrogen monoxide, this also has rotational and vibrational motion. So translational motion is, this molecule moving through space. Rotational motion is it spinning around, rotating in place. Vibrational motion is that bond stretching and contracting. And so this has three different types of motion compared to one for the argon. These are both gases, their molar masses are similar, but we see that NO has a higher entropy than argon does because it's more complex. If we look at carbon monoxide and C2H4, their molar masses are super, super close. But C2H4 has higher entropy. That's because C2H4 is more complex. It has more bonds that can stretch and contract, and so there's different ways to arrange the energy. If we have molar mass and complexity both increasing, then the molar entropy will also increase. So here, comparing compounds between nitrogen and oxygen, NO, NO2, and 2O4, we have molar mass increasing, but we also have the complexity increasing, and we see an increase in entropy. If you dissolve a crystalline solid into solution, that's also going to increase the entropy, because those ions were arranged in a very particular way, and they were close together. They were fixed. They did not have translational energy. So when that solid dissolves, then the energy that was concentrated in the crystal becomes dispersed throughout the entire solution. And so potassium chlorate as a solid has lower entropy than it does when dissolved in water. We can calculate the standard entropy change for a reaction. And this is going to be done just like we did for enthalpies of reaction. You take the entropies of the reactants multiplied by their stoichiometric coefficients, and you're going to subtract that from the products. So here we got this guy. So this is the same form that we saw for delta H. It's probably too fat. No, it's okay. You can put H's in here. Oops, that was the wrong button. So the same form. N represents the coefficient in the chemical reaction, the stoichiometry. But for standard enthalpies, elements had 0, right? Whereas with standard entropies, at room temperature, they are always non-zero, because the only time they are 0 is at 0 Kelvin. And lost again. Okay. So calculate standard entropy change for this balanced equation. And we are given the molar entropies that we need. So we're looking at the entropies of the products, which is like the final, minus the entropies of the reactants. So delta S standard for this reaction is going to be the products minus the reactants. So we have 2 moles of water. So we have 2 moles times the entropy, the molar entropy of water, which is 188.8 joules per mole Kelvin, plus the entropy of SO2. We have 2 moles of that times the entropy of SO2, 248.2 joules per mole Kelvin. So those are the products. This never fits conveniently on a single line. And then we're going to subtract the reactants. There's 2 moles of H2S, and its entropy is 205.8 joules per mole Kelvin, plus 3 moles of oxygen times the entropy of oxygen. So 2 times 188.8 plus 2 times 248.2 minus, good idea to use parentheses here where those brackets are, 2 times 205.8 plus 3 times 205.2, close the parentheses. So this is the change in entropy for this reaction as written. Any questions? Anybody else get that number?